No, for he's got this mathematical program. Let's make use of it. Useful thing. Ooh. Anyway, and then the thing on the carbon nanotubes is pure math. Vectors. You'll see if we get to it. I don't know. This whole polymer world is, how do you mix? Mixing is always a difficult thing. And how do you mix a nanoparticle into, let's say, nanocellulose, which is more a hydrophilic type material? How do you mix it into asphalt? And we did that at AIT. And the students were very, very clever, and we chemically modified, because it's easy to modify nanocellulose because it has so many hydroxyl groups. Right? And it's a good project for you, by the way. You already have your project?
Like in my master's, I did the nanoparticle incorporated bond resin.
In what?
Nanoparticle incorporated bond resin.
What is
my master's?
What is that material you just said?
Like PLA, the polymer is PLA. And
PLA.
Yeah, I incorporated copper and iron nanoparticles.
Oh wow, okay.
And aloe vera too, as polymer.
And you measure optical properties or thermal properties?
The thermal properties and physical.
Thermal.
Yeah, and the biological.
Okay, fantastic. What is your project here?
This one, like I modify with the different polymers. Like I use only single polymer last time masters. So I produce nanofibers using the electrospin technique.
Oh wow, that's very interesting.
Yeah, this time I produce nanofibers with different polymers and incorporate into the nanoparticles and bioactivity.
Oh my God, that's fascinating. Well, chemistry, you have to figure out if things mix. Okay.
Just a quick note.
Yeah.
I did maybe I should keep this as this is kind of like a
You did what?
answer for your homework. So remember the surface to
Yeah, you did. You did the
we
cone?
did it as a cylinder.
Yeah, you did.
I haven't done that. I haven't done the.
So that's the rectangle
So
and the cylinder.
That's a rectangle.
Which one is that?
So this one is a rectangle. It's this blue one.
So it's higher.
It's this is the round one. The round one.
You have to learn these programs, guys.
Actually, I mean, if you like.
So the
Oh,
rectangle,
no.
students are always looking for. Okay, now do the cone.
Yeah, I done.
Okay,
So let's show
you
you.
have a program, you can use a program, you can work in groups. If you get stuck, you should consult with them.
I think they're capable of doing it. So basically, all you have to do is plug in the formula for surface, volume, surface to volume. The key is you have to the geometry stays on the A and H, right? But you want to control for the volume. So what you have to do is make A as a function of H to control the volume, and then you can vary the H. So that becomes your aspect ratio.
Anyway,
Yeah,
you
there you
got
go.
looks good.
But you could do it from the mathematics that we taught you, right?
Okay, guys, so hopefully I've got 2 more lectures. I don't know if I can do both. We'll get through now. We're going to do energy. Okay, this is where we are really important because everything we've done so far will converge now to energy. And we're going to use the cube octahedron. Okay, so that's going to be our model. Surface energy is a function of. Oh, sorry. I have to talk about surface energy is a function of material size, right? We know that already. Surface energy is extensive property, and the bigger it is, the more energy the surface has. but it doesn't have more excess surface energy than a smaller particle. Understand? So it becomes more dominant as materials assume smaller size. Excess surface energy is like the broken bond, right? There's energy that's not there. It's not really extra energy, it's just not there, right? It needs to be fulfilled and saturated. There are many reasons for increased surface energy. In goal 55, we have broken bonds. We already talked about that. In carbon nanotubes, we have strained bonds. There's no broken bonds, but it's strained. We proceed with the surface energy. Surface, sorry. Forgot to spell check. Of gold magic number crystals. Okay, if we start here, and again, this is very intuitive, there should be no history here. If the surface energy of these little cubes is sigma, what is the total surface energy there? You add up all of these cubes, right? 4 times 4 times 4 cubes, 64. It should be 384 sigma, and there's 6 sides to each cube. So there should be a total of 384, whatever sigma is, some basic energy unit, right? If I break it up into these little rectangular solids, it goes to 320. If I break it up into cubes, it looks like a cube, right? It looks like 256. I break it up. I'm not sorry. I'm going to get dyslexia. I'm merging. I'm not breaking up. I'm breaking up here. I'm merging. Every time you merge, what happens? You lose surface, right? I put 2 things together. I lose the surface between them. So I lose 2 sigma on every surface that I merge. So I merge 2 blocks, so I lose, so each of those is 2 sigma, but I lose whatever was in the middle, right? And this just continues and continues on until I have one big block. And each side is simply the surface area of just those surfaces that you can see as 16 sigma times 6. So we go from 384 to 96.
And the energy is giving off to us.
And when it's merging, energy is given off. Absolutely.
So those are like floating.
Hmm?
The ones that are small floating.
It's floating. What is
They're not connected.
They're just floating. The cubes are just not connected. No, they're just in air. Here's one cube. Here's another cube. Just for a picture. These are connected. These are more connected. And finally, it becomes one solid. So every time inside here, you lose a surface, you lose 2 sigma of energy, whatever sigma means. Yeah. Okay. Very simple. So this is just the basics of surface energy. This is the fundamental equation. Energy equals gamma times area. Again, we're worried only about area. Okay, surface energy. Sometimes a surface energy is either gamma or sigma. So if we break up a bulk material and convert it into nanomaterials, breaking bonds requires energy. Therefore, energy is input and has a positive sign. Thermodynamics is very strange in some ways. If you have to put in energy, that's a positive sign. If you give off energy, that's a negative sign. So just remember that. This is why raindrops cool an area, because they're broken up into small pieces as they hit the ground. Note that if material coalesce comes together, energy is given off. Why? Because bonds are made. That's a very strong thermodynamic driving force. Making bonds is what all materials want to do. Negative sign. Okay, so let's figure out quickly how much energy it takes to atomize a drop of water. Apparently a big drop, 100 milliliters. But I was only going to use 10, but it just ended up 100. So 100 milliliters of H2O, we're going to break it up into 100 nanometer cube droplets. we need to know the established surface tension of water. Water has surface tension. The molecules on the surface of water are different than the molecules in the interior, just like in the cube. The cube ought to be the surface atoms are different from the volume atoms. They're different. The volume atoms have 12 neighbors. They're very happy. Surface atoms are very unhappy. They have 5 neighbors or 8 neighbors, but not 12. Right? So they want more neighbors. So surface tension of water means that the water has stronger bonds than inside the water. Why is that? The answer is simple. It's looking for more bonds. When water is inside, it's bonded to a lot of other waters. I think tetrahedrally. All right. On the surface, that's not true anymore. So what it does to compensate, it either tries to make bonds with other things, which is not easy, or it just makes stronger bonds to itself. That's where surface tension comes from. How many have jumped into a swimming pool? It's not easy sometimes. Did you do belly flop? Oh, it hurts. It's because of surface tension. All right. And a submarine can travel faster underwater than on the surface. Okay. Because there's no surface tension underwater. Okay, so water drop, all kinds of water in surface tension. That also drives water to become spherical. It's always pulling on itself, two-dimensional, always pulling on itself. And it's also making stronger bonds inward, so it's compressing itself. So it's 0.7275 joules per meter. That's joule is the unit of energy. Or what we like to do as chemists, physics likes to use that, chemistry likes to use 0.7275 meters per meter squared. Okay, so we have to use this equation. Energy equals gamma times the change in area, that's all. Gamma is constant because it's the surface tension value, but we know the area is going to change. Okay, so we just do our calc again. My favorite number is 4 pi r cubed, 4/3 pi r cubed. We see it everywhere. And we calculate the area. Again, hopefully get it all right. And we find out that the area of the big drop is 0.0142 meters squared. And we like to use meters because we want our answer in joules per meter squared. All right, and then we now, what is this? We calculate the surface area of the small droplet. And obviously very small, -16 meters, -16 to the meter squared. And that's what I'm saying, but now we have to know the total surface, the collective surface area. Because we're breaking it into many droplets. We find out we have 10 to the 21st droplets. So how do we find the total energy? We just simply multiply the number of droplets by the surface. Right, now the next step is simply how much energy. So here we use our joules per meter squared times our area, meters squared cancel, and we have energy, 7.8 times 10 to the 4 joules. For the collective surface area, we just simply total it all up, and we find out that we have 7.5 times 10 to the 3rd joules. Now we do the delta A equation, and we end up with plus 7.58 kilojoules. And that is enough. Again, check the math. I know it's positive, but you gotta check it. Is this enough energy to power a 2-watt light bulb for 1 hour? That's how much it takes to break up 100 milliliters of water into nanometer droplets. Is it wrong? But anyway, it takes energy. That's the whole idea. If I want to break up water, break the door down, that's going to take energy to do that into smaller pieces. That's fundamental in chemistry all the time. you're making and breaking bonds, if I'm doing a cluster and I start with atoms and molecules, there's a process called nucleation, okay? At first, there's an energy barrier, just like there is for just about any reaction. There's an energy barrier and there's entropy involved. Entropy does not like organized structures, right? Entropy likes random structures. So you're fighting that. So you're coming up to the tipping point. And it's either going to go back to becoming atoms and molecules, or it's going to start being a cluster. And once it starts being a cluster, the delta H, which is the bond formation energy, becomes overwhelming. And it just boom, just grows and grows. And it overcomes everything. It becomes bigger and bigger and bigger. Because why? It's giving off energy, it's making more bonds. That's what things want to do. Okay, so here, let's look at the broken bond model. And you already had a little introduction to that. We started with a structure, surface to volume ratio. We understand special configurations and magic numbers relate now to energy. Here we look at excess surface energy as a result of broken bonds. Bonding energy in clusters is the sum of the bonding energy of all the atoms. We calculate the surface energy for cube octahedral FCC metal silver. Silver and gold have the same structure. They determined experimentally that it's 284 kilojoules per mole. Okay, that's where we're starting. That's called the cohesive energy. That's all the energy that's holding the silver cluster together. Okay, now where do we go from here? Well, okay, there's two paths. One, we can calculate the number of broken bonds per type of surface atom. The 111, the 100, the edge and the vertex atoms, right? We can calculate the energy per type of surface atom. So we calculate the type of atom and how many broken bonds. Then we calculate the energy per type of surface atom. Then we calculate and plot the surface energy per atom as a function of shell index K. So all of this is, you've learned the shell index, now we're going to use it again. And then there's different formulas for each kind of atom. The other approach we're going to do is approximate the surface area of the clusters by summing the hemispherical values of atoms. I'm sorry. In other words, we want our answer in terms of per meter squared, right? How do we know how many meters squared? How many meters squared do we have here, right? How do we calculate that? And you're going to find out, depending on how you calculate it, you're going to have completely different results. I figured out that if I just take the hemisphere and add those up, that gives the best result. I can put this inside of a cube octahedron and measure the area of the regular cube octahedron. Use that as my meters squared. Or I can put the atoms on top of a cube octahedron, right? Or I can put the cube octahedron between the atoms. Which one is the best one? That's hard to say. We have to plot it and see. But you'll see it's going to be radically different. You have to be careful. All right, so this is kind of to sum, we want to calculate the energy per atom for each and 4 kinds of atoms. That's what we really want to do first. We're going to use the nearest neighbor broken bond model. And that means that only the nearest neighbor will be counted. So there's in clusters, the electronic structure goes throughout the cluster. So there's nearest neighbors, there's second nearest neighbors, third nearest neighbors, right? We just want the nearest neighbors and the broken bond. So from the surface layer, we can see we only deal with the 111 and 100. That's good. We treat the atom like a hard sphere, like a tennis ball. Only first nearest neighbors, other energy contributions are not considered. There's others, trust me. And surface structure has the same crystal structure as the bulk, even though later you'll see that the surface structure can change because of non-intensivity. And then applicable for metals with magic numbers. So we already know our magic numbers. Okay, cohesive energy we call EB, E sub B. Then the binding energy between two atoms is epsilon B. That looks like an epsilon, but it's not. So they are related as follows. The cohesive energy, the total energy of the cluster, equals the bonding energy between atoms divided by 2. Why do we divide by 2? So we don't count each bond twice. Not each atom, each bond. And then Z is the coordination number. In our case, it will be 12. And A, of course, is Avogadro's number. Nothing new here. All right, so for FCC crystal, Z is 12. 6.022 times 10 to the 23rd. Now we can replace the cohesion energy EB with bond energy in terms of delta H. Delta H is the thermodynamic enthalpy, which really relates directly to bond energy. And then we rearrange the equation to the bonding energy between atoms is equal to 2 times delta H divided by Z times Avogadro's number. Next, we have to calculate the number of broken bonds of each kind of surface atom. We call that surface atoms are unstable due to broken bonds and hence are more reactive chemically. So you look at the 1-1-1 face as we did earlier. You can see here there's 3 on the top and 3 on the bottom. Everyone, I think, understands that clearly. So the 1-1-1 plane has 3 broken bonds. For the 1-0-0 plane, it's the face-centered plane, a parallel plane on each side. You can put another layer on top by just skewing it, right? Looks like what, 45 degrees? And then you can see there's 4 broken bonds on the top, 4 on the bottom. Okay, easy enough. For the, of course, for the, we know already we calculated the edge atom has 5 broken bonds. The vertex atom has 7. All right, so those are the 4. For the so we'll just call this excess surface energy term. I hope you don't get confused by all these energy terms. But the excess surface energy is 3 times for the 1-1-1 atom is 3 times bonding energy divided by 2. Again, we have to divide by 2, right? Because we don't want to count bonds twice. For the 1-0-0 plane is 4 times the bonding energy, and we're assuming the bonding energy is the same for all of them, okay? Divided by 2. For the edge, it's 5 times, and for the vertex, it's 7 times. Okay, we plug those back in. Now we do our excess surface energy. Now, I think I should be more clear about what we call the energy, because I just called it something else earlier. But this is the total excess surface energy of the whole thing is delta H divided by 4 times Avogadro's number. You can see we did the equation for the 1-0-0 plane. It's divided by 3 times Avogadro's number. Remember, delta H in terms of kilojoules per mole. So the Avogadro's number will cancel out the mole, basically. And then for the 7, it's 1.7. So you can see as you're dividing by a smaller number each time, the surface energy is going to be larger, right? All right, so that's that. Now, this is where our stuff comes in. I'm happy that this worked out pretty well. We calculated formulas for each kind of atom, actually. Pure edge atom, a pure inside atom, et cetera, right? We know that there's 12 vertices. For counting, this is for accounting. We know that there's 24 K minus 24 edge atoms. We know that the pure face atoms are 6k squared minus 12k plus 6. And the face atoms, 111, 4k squared minus 12k plus 8. Okay, so we did that earlier. So it's all converging a little bit. This I did with my little kaleidograph program. It was tedious, but nonetheless we did it. And we came up with average energies. Because ultimately we want to plot. Now, I can't recall, Dr. Punjai, if I gave weight to all the average energy. I just think we just add them up, right? If we have all of these different kinds of atoms to get the average energy, we just add them up. I think we did it right. Okay. We add them up and we come up with this curve. This, and I'm using EV now, don't get confused. Electron volts are easier to work with than joules. Joules, I have to go 10 to the minus 19, 10 to the minus 16, but an electron volt is simply joules divided by the electron charge. So you get a much more manageable number, okay? And so it doesn't matter if it's joules or electron volts, that's the curve. So does that make sense? It means that as your shell index K increases, when it's really small, the energy is extremely large. It's absolutely proportional. Absolutely proportional. Until it converges with the bulk value. Then that becomes the lowest value of the surface energy of silver, for example. So our goal is to use the broken bond model now to calculate this curve in terms of joules per meter squared. This is not joules per meter squared. This is joules per atom. Okay, average atom. And it all depends on how you approximate the area. All right, how do we approximate the area? Like I mentioned, we can have a cube octahedron circumscribe the cluster. We can have a cluster enclose a cube octahedron. We can have a cube octahedron bisect the equatorial cluster. Or we can add the hemispherical area of each atom. The last one actually turned out to be the only one. So we don't have to go through all this. You can do it yourself. You can calculate the hemisphere of the silver atom from the diameter, which is 0.288. So the radius is 0.144 nanometers. And it's simply 2 pi squared. Normally, surface area of a sphere is 4 pi squared, but we're only doing hemispheres, so it's 2. Divide by 2. And we get 1.3 times 10 to the 19 meters squared. You multiply that by the number of atoms. In a magic number 20, for example, K equals 20, cluster, the total area is 5.24 times 10 to the minus 16 meters squared. And this means that the energy is going to be for that surface 4,002 atoms. By the way, that's one of the magic numbers. You can see K equals 20, and the total number of atoms is 4,002. Okay, so I did this graph myself. Very tedious work. I didn't help with computer programming. But so we multiply the energy. We came up with 5.946 joules, and then we divide it by the area. And what do we get? We get 1.141 joules per meter squared. Well, it turns out by simulation and experiment, the results are very close to that. Honestly, I'm not cherry pick. I did cherry pick. There are other results that were not so close. I'm being honest. As scientists, you should never cherry pick. You know what I mean, right? You pick out the nicest values that fits your data. But I did cherry pick. There's other data that weren't so good. But it's within 1.5 or 1.4 or something like that. It's still close. I mean, within an order of magnitude for such a simple approximation. Anyway, so you look at this, and in terms of the experimental, we were off by about 8%. And in terms of the simulation, we were only off by about 2.6%. So that's not good. Let's see how this looks. On the right, you can see our simulation. This was the atom joules per meter squared. Oh, how did we do that? I think this was the original one. I did this by another method. And this was done with the hemisphere method. Oh, here. Joules per meter squared just by K. This was joules per meter squared by K plus 1. And this was an inscribed. You can see these are totally off base. There's no way the surface energy is going to increase as particles get larger. Just totally artifactual. This one was closer, but this one was the best. The result was very much like the one we got with using only K's per atom. So anyway, we went from a geometric figure to actual energy and got a good approximation. And these, like I said, this is just taken from crunching all the numbers of K 1 through 20, and you can see as far as Sheldon asking. The larger it is, the smaller the surface energy. That's it. That's a simple message, but it's very important in nanotechnology. All right, last thing here is mitigation. Let's see how we're doing. Well, we have a little time. Okay. Everyone okay on that? That's the natural trend, and that's what should have happened, and it did. Just by a simple, what's called the nearest neighbor broken bond approximation. All right. So mitigation of energy. What does that mean? That means how do nanoparticles compensate for their energy, their excess surface energy? They can rearrange. The surface atoms can shift and dip into each other more. They can contract. When you contract, you're taking more electrons from the volume to stabilize your surface. You can become more symmetrical. Remember, we know that stabilizes the surface as well. Particle shape, S surface to volume ratio can decrease. Achieve higher symmetry forms, become more spherical. Particle fusion, coalescence, aggregation, agglomeration, nucleation. This process called also ripening, which is just like what I told you, the crystal just gets bigger and bigger. Compaction and sintering. If I compact something, I'm going to reduce the total surface area. Kinetic methods, of course, you can isolate them. You can ligand stabilize them. Make more bonds with the surface. Electrochemical or steric repulsions, low temperature storage. These things inactivate the active surface. So they do all that. Nanomaterials go through all these processes. That's why I'm saying the density of a nanomaterial may be very different from its bulk density. It may become more dense. Coalescence is the same kind of material coming together, like water droplets, yeah. The big particle is more stable. Aggregation is like different crystals aggregating together. This is just very specific definition. Agglomeration can be just anything coming together. Nucleation, from atoms and molecules, you become more stable as you nucleate and become bigger and bigger. Oswald ripening is becoming bigger at the expense of smaller things. Now that's also true in life. Rich people get richer, poor people get poorer. Compaction and sintering. Compaction is pressing things together, and sintering is thermally compressing things together, and you make material with lower surface to volume ratio.
These are, I guess, this is getting beyond the nano realm, right? Because you kind of,
If you get bigger, if you get bigger, you become micron sized, and you're out of the nano range. You're more stable, but you're not useful anymore. We want to be a catalyst. A micron particle will not be a catalyst because the surface is not reactive enough. So you go out of the range of usefulness.
gotcha.
in the polymer world, if you become micron size, you may not want to use that for interfacial bonding.
So whereas before the break, when we focus on say surface to volume, that's something that we say want to maximize. Whereas after the break, the energy, it's just happening naturally, and we kind of try to go away from that, try to reverse.
Well, actually, we want to surface to volume energy, excess energy is something we want. That's responsible for all the properties of nanomaterials. Okay, that's what's responsible. If we lose that, we become just another boring bulk material. And so we want to have small particles. Remember living on the curve, right? The catalyst is active only at a certain size.
And the trick of the trade is to kind of stabilize that.
To quench, for example, I want to make a quantum dot that fluoresces red. I have to quench it at a certain size. I can stop the reaction by adding ligands. And so the trick is I want to keep gold 55 very small, but it wants to get bigger.
Yeah.
So I have to stop that reaction by adding the triphenylphosphine ligand. So this is the trick of nano. You have to.
Engineering comes in.
I want this reactive, but I don't want it big. I don't want it too small. I want to stop it.
And in practice, you can sort of like measure how successful you are at arresting this growth, right?
Exactly. We want to bond something to it. For the catalyst, we have high temperature that keeps things from bonding to it, but it also keeps it from going because it's isolated. Remember, one of our things was isolation. Catalyst is usually supported on some kind of oxide. And it doesn't grow, it doesn't shrink, but it's just very reactive. Okay, one last thing. We'll do a little bit of it. I don't know if we can do all. Let's see how much time we have. Yeah, we've got just 8 minutes. Okay, we'll just kind of cruise through this. We're going to look at carbon nanotubes. Pure tubes made of carbon, graphene sheets. Carbon nanotubes are very important. I mean, if you're into sustainability, I don't know how much, if you're into more the social side of sustainability, the government, the management, or you're more on the technical side, the computer side of sustainability. This is for the technical side, but you need to know about it still. Even if you're a manager, you say, well, what about we can use carbon nanotubes or whatever metal organic frameworks to remove CO2. You're the manager and you know about it. The guy says, oh yeah, that's a good idea. Let's give it a try. But even though you're not a scientist per se, you know about it. Well, I read about metal organic frameworks and it seems to remove CO2. Can we do something about it? It's a project. Graphene sheets, they have resonant electronic structures, so they align in a magnetic field or electric field. And isotropic properties. And isotropic means different direction properties. They can conduct heat only along the tube axis. A lot of computers are being cooled by carbon nanotubes because they remove heat from the source without a fan. Okay. Conduct electricity only along one direction. They're used in now nano devices. Ballistic electrical conduction, we've done tensile strength filler for polymers. Okay, carbon nanotube can be grown. There's a catalyst particle, usually iron, nickel, or cobalt. And carbon approaches, methane, CH4, comes to the surface of the catalyst particle and decomposes. Decomposes into carbon and hydrogen gas. And the carbon goes into the particle and saturates it, but after a period of time, stuff starts precipitating on the surface. Isn't that the nanoscale? It's amazing.
I had the wrong impression. I thought nanotubes are like pasta with an open end.
They will. We're getting there. Oh, that's what happens over there. So these form on the form was called a folding cap. Then the cap starts lifting off and more carbon is decomposing. And then it started growing. It's got a cap. You can remove the cap. And you have open ends. You can do a lot of things with it later. But that's how you grow it. You grow it at higher temperature, like 600 C, in methane and argon gas.
And then you can grow the nanotube on a catalyst. Okay, vectors quickly. A1 and A2, we're going to go through just quickly here because we have just a few minutes. A1 and A2 are two vectors that define the two-dimensional graphene. Second thing to know is that there are two atoms per the unit cell. So the vectors here define the unit cell for graphene. It could be the hexagon, but that's not a unit cell. This is the unit cell. It's a rhombus or parallelogram. There's two atoms here too, if you can add them up. So anyway, remember that? Remember that. Because what we're going to do is unfold the carbon nanotube. This is the graphene sheet. We're going to unfold it, lay it flat. So there's three kinds of tubes. One is where the longitudinal direction is along the apex of the hexagon. The other one is where, oh, I made it wrong. Oh, no. This way, yeah, this way's wrong. It's correct. But this flat part is along the tube axis. And the third one is everywhere in between. These are called chiral tubes. So the symmetry is broken down significantly in depth. So the zigzag tube is a chiral angle because it's the reference. It's called 0. The chiral vector and the nanotube is defined by this vector, CH equals N and M. Two indices define the nanotube. Running out of time. I'm not going to make it 4 more minutes. Okay. Okay. So each, just like any vector is defined by the two basis vectors, A1, A2, the two indices N and M. And that's actually going to be the circumference of the nanotube. Okay, CH. As you go along the tube, you can see 0, 0, 1, 0, 2, 0, 3, 0. As you go this way, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. You go back, and you can see that if N and M are equal, it's called an armchair tube. If N equals 0, it's called a zigzag tube. And anything in between, 30 degrees is the maximum of this angle difference. Okay. Okay, so this is cool. So we make a nanotubes. I can do what's called a 4-4 nanotube. And notice I can go 1, 2, 3, 4, right? And then 1, 2, 3, 4, just like any vector addition. And you get CH, which is actually will be the circumference of the nanotube. If I take the black dot there and the black dot there and fold them together, I get the nanotube. I wanted to do that, but we didn't have time. All right, you can fold it over. For a 4-0 tube, I just go 1, 1, 2, 3, 4, and then 0 this way. It's going to be a zigzag tube, right? I do a 6-4 tube, that's this one. 1, 1, 2, 3, 4, 5, 6. 1, 2, 3. Oh, 1, 2, 1, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. And if I do a 3-7 tube, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. That's all there is to it. So that's just basic, very similar vector additions. Now, what can we do with that? Okay. I didn't go through you can do inner dot products and cross products and all this stuff to get all these equations, but I'll just show you quickly the equation. The diameter is just simply A0, which is the magnitude of the basis vector, divided by pi, times this breakdown of n squared plus n plus m squared. The chiral angle is there, and the circumference is there. Okay, it's ID, right? So we build a nanotube, let's say a 6-3 nanotube. We got 1, 2, 3, 4, 5, 6, 1, 2, 3. There's your chiral vector this way, 6, 3, okay? And I put A1 and A2 in those directions. You can put them in any direction. So there's the origin. It was it, and there's one more parameter, the translation vector. And again, In my book, I have all of this stuff derived with all the vector multiplication, T1 and T2. DR is the greatest common divisor, and from that you can calculate the actually look maybe the number perpendicular to the chiral vector. You fold it over and you have the unit cell. The unit cell for the carbon nanotube is huge, because especially for the chiral nanotube, it's very huge, many atoms. Okay, you see, boom, put together, we're almost there. The number of hexagons is just area, right? Cross product A1 times A2 is the area of the rhombus or the unit cell, and the n hexagons is simply the area of the T times the diameter times the height divided by the area of the rhombus. That gives you the number of hexagons. The number of atoms, and 2 atoms per, we just simply multiply hexagons by 2 because we know there's 2 atoms per hexagon. And then we start building our nanotube. Here's how it looks. Now, oh no, we never did put that's it. Okay, we're done. I did an example of it, but I forgot to upload it of a 60 nanotube with all the parameters. The diameter 19. Okay, guys, that's it. We're done.
So in the, I guess in the frontier space, where they're competing with nanotech companies,
Oh yeah.
they try to simulate all this and try to
Right
experiment with it.
Right now, simulation is one of the most powerful tools in research labs. That's what I'm saying. If any of you guys are crazy about computers and simulation, you should know. I think everyone should know basic programming and some of these, like Mathematica or MATLAB. MATLAB is again another great program to solve a lot of equations. You may need them, even statistically, if you're management or other kinds of things. So this kind of stuff is just fundamental nanotechnology. You had, of course, yesterday more qualitative approach about what nano is and where its place in society is and all that. And today we had a little more quantitative approach to understand really what it's about. Now you got at least I know fundamental understanding of what surface area means and sort of how it converts to surface energy in terms of nanomaterials and their properties. There's of course a whole year of coursework you can do nano, of course, many different courses. Just to be aware of what's going on. May help you.
If they're, let's say they're good at modeling and simulating the properties, so you help with the nano engineering, you still need the sort of the physical lab skill, right? Is that very hard to pick up?
Nano is like polymer chemistry. You make it in a lab. The materials are made and dealt with in a lab. You can do it like I told you about Material Studio. You can, from quantum mechanics, you can make materials now, and then use finite element methods to test them. It's just unbelievable.
Like, would it be feasible? Let's say, with our lab upstairs, we have a little basic wet lab. Very simple.
You can
this
make
guy grow some
nanoparticles are the easiest thing to make. It's so easy. It's that thing easy. It's called bottom up. From chemistry, regular chemistry. Professor Hornyak is a chemist.
Yeah.
So she knows how to do all that stuff. So anyway, that's it, guys. Okay, so enjoy. You guys do well. You're gonna have a great program here. See how what the future brings. It's crazy. We talked about the augmented age, and oh my gosh, Professor Warsack, we were talking about AI and all the things that come along with that. So, good luck. That's all I can say. Okay, thank you. Guys. Thank you. Okay.
Yeah, so if you into this sort of thing, you have to go to a demo, and then go. Because she's already setting up the wet lab for.
Yeah, she's got. I saw some